Today we'll start off with a quick example in doing uh, trying to diagonalize matrices, and that has a lot to do with eigenvalues and eigenvectors. So this is one that discusses multiplicity in particular. After this, we're going to backtrack to 3.3 and quickly talk about Kramer's rule because I think that's a quick and easy um, application for determinants. And then we'll talk a little bit about um, top three stuff, finding areas of parallelograms and volumes of parallelepipeds. And then we'll jump back to section 5.4 and talk a little bit about how things apply to linear transformations. Let's see if we can do all that. All right. Yeah, I know. Sorry, we're jumping around. So this is kind of like this would fall in section 5.2 ish, 5.1, 5.2 ish, five. Yeah, this particular problem. Um, and then uh, like I said, we'll go to 3.3 and then come back to 5.4. All right, it says here, find H so that the matrix A is diagonalizable. And this is an upper triangular matrix, so the determinant of this is going to be easy. It's just the product of the diagonals. Okay, so that's a good start. What we want to do is we want to find the determinant of A minus delta or lambda I. And then this sets up our characteristic polynomial. So if we subtract the lambda I, you take your diagonals and subtract lambda from each one. Zero. And then if you take a look at the product of the diagonals, right, that's a determinant for an upper triangular or any triangular matrix. Then it's just going to be 4 minus lambda. That's a factor that happens twice. And then we have 1 minus lambda and negative 1 minus lambda. So we have lambda is equal to 4 multiplicity 2. We have positive 1 and we have negative 1. So these are our eigenvalues. So given these eigenvalues, we can find corresponding eigenvectors. I don't want to go through all of them, but I want to focus on the 4 has multiplicity 2. And so yes. Yes, well, I just multiplied the diagonals because it's an upper triangular matrix. Your determinant is just the diagonals, the product of the diagonals. So now that we have this, let's just focus on lambda is equal to 4, and we'll see what's going to happen. So when lambda is equal to 4, we want to find a basis for the null space for a new matrix, and that's when you put 4 in for lambda. 4 minus 4 is 0, negative 3, positive 6, negative 1, 0. 1 minus 4 is negative 3, h 0, 0, 0. 4 minus 4 is 0 again, and 0, 0, 0. Negative 1 minus 4 is negative 5. We want to find the null space for this. Solutions to the homogeneous system, or whatever, however you want to say it. There's a lot of different ways to look at it. And for this, I want to, we could probably skip a few steps here and there. I think we can just multiply the first one by -1 and add it to row 2, and then we'll multiply, I guess we can multiply this by 1 and or 3/5 or whatever, 5/3, 3/5, 5/3. So we're going to get 0 minus 3, 6, -1, 0. This would be 0, and we're multiplying the first row by -1, so that's h minus 6, 0, 0, 0, 0, 3, 0, 0, 0, 0. Oh, so that should be a 1. Okay, so I think this is already in a row echelon form, and so we're going to notice that there's a one free variable at x1 is free. If and if h minus 6 was 0, then that would be free also. If h minus 6 was equal to 0, then x3 would be free. So we see that x1 is free, and we can say that if h is equal to 6, then x3 is also free. And if it's not equal to 6, then we're going to get a value for this, and then we're only going to have one eigenvector. Okay. So should we try to spell out both cases? I mean, look at it carefully. So let's assume that h equals 6 here. Maybe we should do this in a different color. So if h is equal to 6, then we're looking at the solution to 0, minus 3, 6, -1, 0, 0. H is equal to 6. This would be 0. And then 0, 0, 0, 3, 0, 0, 0, 0. So we can go one more step and knock out the 3. And then we get 0, minus 3, 6, 1, -1, 0, 0, 0, 1, 0, 0, 0, 0, everywhere else. So if you solve for this, we're going to get h, or x4. x4 is equal to 0. x3 is free. x2 is equal to, well, minus 3x2 plus 6x3 minus 1x4 is equal to 0. So x4 was equal to 0, x3 is free, and so we can solve for x2, positive 2, x3. Is that right? And x1 is also free. So if this was the case, then we can conclude that your solutions, x will equal to x1 is free, x2 is 2x3, x3 is free, x4 is 0. So your solution would look like that, but you can break it up into a couple of vectors. one that's being multiplied by x1, and another one that's being multiplied by x3. And then those will turn out to be your two linearly independent vectors that span the null space. Yeah. Oh, because I would set, if I'm looking at this zero, the row full of zeros wouldn't make sense or wouldn't help. I guess I should be looking at this. We got two rows of zeros, and then you would set this, because you're looking for the null space, you'd set each of these things equal to 0. So x4 is equal to 0. Yeah, I have this extra arrow here. So we have a couple of solutions, or we have a couple of vectors that would span the null set, and those would be your eigenvectors. So you have two eigenvectors. So the eigenspace vectors, there's two of them for lambda is equal to 4 is going to be given by these two vectors. Yeah. Well, not necessarily, because we have multiplicity. So I would call this the algebraic multiplicity. So that's algebraic multiplicity 2. In this case, we would call this a geometric multiplicity of 2. So if all the eigenvalues with more than one of multiplicity 1, if they have the same multiplicity for their geometric multiplicity, if they have the same number of eigenvectors as their multiplicity, then you can say that the matrix is diagonalizable. So in this case, it's diagonalizable if the multiplicity for if the number of vectors matches the multiplicity. If h does not equal a 6, so let's pick any other number aside from 6, like 0. 0 is nice. Then you're not going to get two eigenvectors for this, and we'll see that happen. Yeah. If the number of eigenvectors is the geometric multiplicity. So if the number of eigenvectors don't match the algebraic multiplicity, then it would not be diagonalizable. The algebraic multiplicity is the multiplicity from the characteristic polynomial. Yeah, when you find your lambdas, here we had lambda 4 minus lambda squared, so that had algebraic multiplicity too. Therefore, the matrix is diagonalizable. Well, it's not diagonalized yet. In fact, we have to find the eigenvectors for lambda is equal to 1 and -1 if we want to fully diagonalize it. Oh, find h so that, yeah. So we found h. Right. And I'm not going to diagonalize it. But you should, for practice sake. Yeah. Yes. 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 And let's do that. What if h does not equal a 6? And let's let h, at this point, we can randomly choose any other number aside from 6, like 0 is a nice number. So let's let h equal to 0. And we have, I'm just going to copy this matrix over here. 0, -3, 6, -1, 0, 0. Wait, that's not what I want to copy. I want to copy this. 0, 0, negative 6, 1, 0, 0, 0, 3, 0, 0, 0, 0. So if H was equal to 0, this is the matrix that I would be trying to find the null space for, which is already in row echelon form. So I can just see that there's one free variable here. And if I take a look at what happens to the other variables, I have 3x4 is equal to 0, so x4 is equal to 0. And then we'll see that x3 is going to equal to 0, and x2 is also going to equal to 0. Okay? So x3 is equal to 0, and x2 is equal to 0. So then I only have one vector here to span the null space. So the null space for this is only one dimensional. So eigenspace for this would be the span of these two vectors. Eigenspace for this is only one dimensional, is the span of this only one vector. So because we have one eigenvector, I don't have the same amount of eigenvectors as eigenvalues if I count the multiplicity. So I had 4 eigenvalues for lambda is equal to 4 is counted twice. But I would have this eigenvector, and I would have 2 more eigenvectors from 1 and -1. And so I won't be able to diagonalize it. If this was the case. Okay. So again, a good exercise for you would be to carry on with this problem, assume that h is equal to 6, and find the eigenvectors for 1 and -1, and see if you can create the diagonalization. So you need the diagonal matrix 4, 4, 1, -1 in the diagonals, and then you would need that invertible matrix that's made up of the eigenvectors. Okay. All right. Any questions? All right, let's move on to, I didn't adjust the page on that first one. All right, let's talk about Kramer's rule real quick. This is one of those rules that's usually covered in, I don't know, in algebra or something like that. What? I don't know. You've seen this in kindergarten, didn't you? All right. So this is a nice compact way of saying that if you have a system that you're solving for A, x is equal to B, then the solutions would equal to each x value in your vector that you're solving for can equal to the determinant of a couple of matrices. And it's going to be divided by the determinant of the matrix, the original matrix A that you get out of this. And then the matrix on top is going to be, this notation is a weird notation, but what this notation is replace the ith column of A with the vector B. So B is the right-hand side of your system that you're solving for. Okay. So it might seem like it's more work than what's really needed in, for example, our first example that we're going to look at, but it also holds a more theoretical approach of trying to solve for systems that would be useful in other areas like differential equations or other things. So let's see if we could apply it to a simple problem like this one, which we could probably almost do in your heads, right? I can do it in my head, but I can't. So anyways, how would we solve for this? We're solving for x and y, and so we're going to let a equal to 1, 1, 1, negative 1. And then we're going to figure out a1 is going to be, yeah, so the same matrix, except I'm going to change the first row. This is like, because this is like going to be for the x or x1. I'm going to change the first column, not the first row. I'm change the first column with the right-hand side vector. And the right-hand side vector is 4, 6. Yeah, but I extended that homework, by the way, because technically we haven't gone over it. No, just three. And the second one would be the same matrix A, except I'm going to change the second column into 4, 6. So the first column was 1, 1, and the second column will become 4, 6. And so if we find the determinants of each of them, determinant of A is going to be, let's see, negative 1, minus 1, negative 2. Determinant, actually, I'm going to just start using the absolute value. So the determinant of A1 is going to be negative 4 minus 6, negative 10. Negative 10. Determinant of A2 is 6 minus 4, 2. So then x is equal to A1, determinant of A1 divided by determinant of A, which is negative 10 divided by negative 2. And then the y would equal to a determinant of A2 over determinant of A, which is 2 divided by negative 2, which is negative 1. And if you plug those in for x and y, you'll see that it does work. And so we found the solution quite easily. Yeah. So A1, it's the matrix, it's the same matrix as A, except for the first column, I'm going to replace it with 4, 6. And then the second one is the same thing as matrix A, except the second column will get replaced by 4, 6. Okay. All right. Well, so that was a pretty lame example because we could have done that easily with what we already know. But now let's take a look at another example where you're solving for functions. So taken directly from differential equations, at some point in some differential equations systems that we're solving for, we're interested in finding u1 prime and u2 prime. And along the way, as we're solving for this, we came up with a couple of systems. So your variables that you're looking for are the u1 primes and the u2 primes. That's like your x1, x2, or whatever. And you have to treat y1 and y2 as if they were just constants, but they're really functions. And you have the 0, and then you have another function f on the right-hand side. Yeah. What's the Wronskian? Well, it's not easier. I mean, this is exactly the Wronskian. Yeah. Actually, we'll see the Wronskian come out of this. So we could treat all of them as functions 0. I mean, even 0 can be a 0 function. But yeah, these are all functions that we would be solving for an example. Yes. No, this is variations of parameters in ordinary differential equations. You remember that because you had a great teacher. Didn't you?
Yes, it's all coming back to me. I remember it's wonderful.
It's all right, you don't have to remember anything.
Doing a Wronskian 3 times in a row for an hour, and eventually the computer, I realized, wanted capital C's instead of lowercase c.
Oh, well.
It's wonderful.
Sorry to hear that. So anyways, what we want to do is if we want to figure out your A matrix and in your A1, your A2 matrix, let's see if we can pull it out. Remember that the variables are U1 prime and U2 prime, right? So those are like your XY or your X1, Y1. And then everything else would be the coefficients. So your A would equal to just y1, y2, y1 prime, y2 prime. And people who are taking differential equations would say, hey, that's the Wronskian. A1 would be essentially the Wronskian, or this A matrix, except we're going to replace the first column by 0 and f. And A2 would be the same thing, except you're replacing the second column with 0 and f. And then you find determinants. So the determinant of this would be y1 minus, oops, that's times y2 prime minus y1 prime y2. Not much to simplify there. And I think people call this the Wronskian. You can write W for that, or you can just write that whole thing. But A1 is going to give us a 0 minus f times y2, and A2, the determinant, would give us y1 times f minus 0. And so we'll see that u1 prime is going to equal to a1, the determinant of a1 over the determinant of the Wronskian, so negative f y2 divided by the Wronskian. And then u2 prime is the determinant of a2 divided by the Wronskian, so that's y1 times f divided by the Wronskian. That's essentially what you're solving for, yeah. Yeah. So this is kind of working backwards, but yeah. So you have y1, y2, y1 prime, y2 prime, uh, u1 prime, u2 prime, 0. Yeah.
Started to come back.
What? Yeah. I'll take I'll take familiar, or it's starting to come back.
You don't do a lot of this in like your day-to-day life.
No. Yeah. But who knows? You guys are doing some engineering problem, and all of a sudden something like this might come up and say, "Hey, that looks familiar." It's all going to come back to me. All right. So in any case, we found solutions, and if these were actual functions, and then you were working with this in a differential equations class, you would continue to solve for this by finding the antiderivative of u1 prime and u2 prime, and then you'll do more stuff to it to get your solutions. But this is a differential equations type of problem. But in that bigger problem, we're using Kramer's rule, and Kramer's rule is one of the better ways to find solutions to a system that might not be all like nice numbers like we had up here. If you have a more complicated system that involves a bunch of other things, then this would be the way to get to it. All right? Any questions? All right, good. Move on. So we're still in section 3.3. Well, it was in last year's test, in last semester's test. Well, I don't know. I mean, it's free game now, right? Yeah, you're not gonna take any integrals or anything like that. You just need to use Kramer's rule to find solutions. That's all. So there's a couple more parts in section 3.3 that kind of lends itself to some Calc 3 stuff. And so the parallelepiped business is what's covered in 3. But this also goes back to a simple two-dimensional problem where the area of a parallelogram is going to be determined by the columns. You can make the parallelogram is really determined by two vectors, and then the other two sides to your parallelogram would just be parallel to those two vectors. And so, given two vectors, you can find the parallelogram, the area of the parallelogram, by setting the vectors as columns and finding the determinant of those columns, which is pretty interesting, I think. It's nice and simple. And so for that, let's do an example. We might even get a visual if we stay in 2D. um, I don't know. No, the hypercube is called something, tesseract. So I don't know. Oh, what movie? What's a tesseract? Oh, I'm not connected to the internet. Any, anyways, whatever. Let's move on. Parallel tesseract. Oh, it's a wrinkle. It's like something to do with time and space continuum because it's like a fourth dimensional thing. Yeah. Okay. Anyways, all right. Let's take a look at this parallelogram. See if we can find the volume or the area. Let's see. We got 0, -2. We have 5, -2. 1, 2, 3, 4, 5. We have -3, 1. 1, 2, 3, +1, and we have 2, um, 1, 2, and 1. Does that look like a parallelogram? Okay. All right. So it looks like we have a vector, two vectors. If we can find two vectors to define our parallelogram, and you have four sides to choose from, and if you take the directions, you have 8 possible vectors to choose from. But if we look at um, if we look at two vectors and make sure that we're picking the correct two combination vectors, then we should be able to find the volume, the area of this. So this vector connects 0, -2, and 5, -2. And so what's this vector going to be if we subtract these two vectors? Depends on the direction, right? So it kind of matters which direction you are because then you might get the other parallelogram. So I think it's head minus tail, so it's 5 minus 0. So that's a +5. And -2 minus -2 will give us 0. And so this is the vector 5 minus, or 5 comma 0, or I guess it doesn't really matter how you write the vector. Um, no, we seem to be writing vectors as columns because we're going to write it as a column. So that's one vector, and then the other vector would be the difference between these two, right? This is where you kind of have to be careful about which difference you're taking. So it'll be the difference between these two vectors. And so this vector would be -3 minus 0 and 1 minus -2. That's a +3, I think, yeah. And if you put this in standard position, you should see that that's the point that the vector is pointing to. So it looks like the x is negative and the y is positive. So it looks like it's right. So depending on which one you put in which column, the switching of columns will just give you a factor of a negative sign. So the determinant here is they specifically put determinant of A, and then they put those bars in front to say it's the absolute value. So this bar represents absolute value and not the determinant, because otherwise they would have just put A with those bars, and that's the determinant. But determinant of A with the bars makes sure that it's positive, because there's a possibility that this might be negative. So the area is going to be given by the absolute value of the determinant of A. And again, it doesn't matter which order you put it in, because if you switch it, you'll just get a negative of your answer, and you're going to take the absolute value anyways. So this would be 15 minus 0. And what you could do is you could check by geometry. I don't want to check by geometry, but the area of parallelogram is base times height. The base is 5 clearly, but then you have to figure out what the height is. And if the height is 3, then that's, we're done. Okay, so that's not a big deal. The next one is just taking the determinant of 3 by 3 matrix. I don't know if we should bother doing that. You guys can do that. If you have taken pre-calculus, if you have taken calculus 3, you'll see that oh, I guess I shouldn't. So determinant of this 3 by 3 matrix, it's called a triple product. It's a cross product and a dot product combined. Um, so from calc. Well, I mean, this is. I think if we'll do an example. Well, you don't need calc 3. It helps if you know it, and all it's going to do is make you think back and say, "Oh, I used to know that," or "It's starting to come back to me," or what did you say? You said, "Oh, that looks very familiar," and then not very, and the conversation that they had there. I mean, that's like that's like taking or having taken differential equations versus the people who've not taken differential equations. Um, why don't I erase this Calc 3 business? So it's not about your teacher, huh? So a parallelepiped is essentially a 3D parallelogram. So without sticking to these particular vectors, because it'll be hard to try to draw this in 3D, let me just draw a random looking parallelepiped, and a parallelepiped is defined by essentially 3 vectors. Just like a parallelogram is defined by 2 vectors, a parallelepiped is defined by 3 vectors. And what we could do is we can take 2 of them and create a 2-dimensional parallelogram, and then extend that to the third one. And it's basically a cube or a box that has been skewed a little bit, but the opposite sides remain parallel to each other. So can you picture this? This is your standard parallelepiped. Standard, generic, your usual, your run-of-the-mill, your arbitrary parallelepiped. And they're going to be spanned by 3 vectors, and provided that those vectors are linearly independent, your determinant's going to not equal to 0, etc., and all the other long list from A to S, or whatever it was now. So the area, or in this case, we're looking for the volume now. The volume of this is going to be equal to the determinant of these 3 vectors. So 1, 3, 0, negative 2, 0, 2, minus 1, 3, minus 1. And the order doesn't matter because we're going to take the absolute value of the determinant anyways, because switching the orders of them may produce a negative sign somewhere. And so if you want the positive quantity, you just take the absolute value, and it doesn't matter what vectors you place in what position. And also, we don't need to talk about this, but the transpose is equal, so you can put these as rows, and the idea of the triple product in Calc 3 looks at these vectors as rows instead of columns. But in any case, let's just find the determinant of this. Actually, this is the problem. You can find the determinant, right? What is it? What? Negative 18? and the absolute value is going to be 18. So I'll put a little stars here and say, you figure it out. I mean, somebody used the calculator. Calculator. Okay, but you can do this by hand, right? You know, just expand on a row or a column. So no calc 3 needed. The calc 3 was just the, hey, remember back? All right, well, there's another theorem here where I know for sure people in calc 3 wouldn't remember. And that's the Jacobian. Yeah, yeah. You remember? Oh, sorry. Some people remember. um, so this is where we take a this is where we actually take a linear transformation. Yeah, this is still 3.3. You hate the section? Well, wait, we're not done yet. More of 3.3 to hate. I hate this section. What kind of crap is that? Come on. All right. I guess. All right. So what's going on here now? Geez, I don't know. Let's take the 2 by 2 example. We have t as a transformation from R2 to R2, and it's a linear transformation. So let's see if we can draw pictures. I don't know if that'll make people feel better. What? I don't know. Looks like it's a sad picture already. So we have a transformation going from R2 to R2. Let's say um, this is XY, and let's say this is UV. So we're going from here to here, and let's say we have some area here. May be easy or may not be easy to find, and another area here. So if this is your domain, D, and this is your codomain or your image. So everything in D gets mapped exactly to everything in this matrix here. Oh, sorry, they call it S. S. Let's call it S. So the image of S here is actually T S. So when you put all the vectors or all the points, you can call them points or vectors, but you take all those points in S and put it in T, it's going to get mapped into this thing. So what are they trying to say? So the area of this area of T of S is going to be related somehow to the area of S. And they won't be exactly the same because the transformation is going to do something to change it. So even though they won't be exactly the same, what we can think about is that there's a change that is going to be, there's a factor, and that's going to be the determinant of A. What's A? A is a transformation matrix. So the T here has an associated matrix. It's a transformation matrix A that's going to help compensate for that change. Okay. And the general idea and why this would be useful is that maybe in this XY world that you're living in, you have a complicated looking area that you need to find. But if for some reason, you're able to find a transformation where the area that you start with is a nice simple area that you can find, then if you want to find this area, then it's as easy as finding the area of S, which hopefully would be easier than finding the area of T of S. And then all you have to do is multiply it by the transformation, the determinant of A, an absolute value of that. Because again, you want it to be positive. Yeah, well, that's what you're thinking about. But the transformation actually goes from the simple area to that more complicated area that you start with. So this is the more complicated area that you're given with from the beginning. Your transformation doesn't actually go from that area to the simpler area. Your transformation actually goes from the simple area to the area that you start with. So this is usually what you're given. You're given this information here, and then the transformation comes from something simpler. Yeah, and you're finding the area of the simple one. A lot of times you'd probably be given T, and then you can find A that way. The determinant of A refers, it's not referring to any of the areas. The determinant of A comes directly from the transformation itself, from the function itself. What? Yes, it is the Jacobian. Thing. Yes, you did. Good job. Well, it wouldn't. It maybe it would be something that you calculate from the previous area or the previous example. But let me see if I have any problems here. Let's try to do number 27. So number 27 doesn't imply anything about calculus 3 stuff, but this is really a useful theorem for calculus 3. And if for simplicity's sake, actually, I don't know if this is simple because the transformation that I was thinking about would be the polar coordinate transformation, but that's not a linear transformation, and so the derivatives make it linear, but that's another story. Another story for another time. If you take my Calc 3 class. Mhm. But I'm not teaching it until like next fall. Oh, too bad. All right. So let's use this information to find the determinant or to find the transformation. So S is a parallelogram determined by these two vectors. Compute the area of the image of S under the mapping of this. So they gave us the matrix already. Sometimes they might give you the transformation itself, in which case you would have to find the matrix. But let's say that um, this comes from the transformation, linear transformation. And it's already given to us, but we'll use it. But be aware that you might just be given the linear transformation itself, and you have to find the matrix, which is something that we've done in I don't know. Oh, before the test, because it was on the first test. Yeah. So what we have here is in our UV world, we have this vector or these two vectors, um, -2, comma 3, and -2, comma 5. I messed up my parallelogram. Well, imagine there's a parallelogram. There's something that happens on the left side of my screen where it just, if I draw, and then, so I mean, I'm not doing that. It just happens. I don't know. There's a margin there that I can't pass, and if I pass it, something bad happens. So anyways, I have these two vectors, b1 and b2, and so this is my S, and I want to find the area of S. So from the previous theorem, it says I could just put them in a thing and find the determinant of that. So area of S. Well, before we do that, let's complete the big picture here. There's a T here when associated matrix A that gets mapped into um, another thing, which we'll worry about later, but let's just say blah. So this is T of S. Yeah. Oh yeah, yeah. We could do that by applying this. Okay, I didn't want to do it, but let's do it. No, it's okay. So to find the image, we need to figure out what happens because the linear transformations take parallelograms to parallelograms, and in calculus talk, it takes the Jacobian takes tangent lines to tangent lines and stuff. So it'll remain a parallel. It'll still be a parallelogram of a different shape. So how is this parallelogram going to look like? T of B1. We're going to figure out where B1 goes. T of B1 is going to be A times B1. Let's uh, let's be tedious about this. And so that's 6 minus 3 minus 3, 2, applied to the B1 vector, -2, comma 3. And then so that's, what is it? -12 minus 9, -12 minus 9, 12 plus 9, 21, -21. And negative 3 times -2 is positive 6 plus 6, so that's 12. So -12 comma 21 So negative 12, 21 would be a vector that's like this. So this B vector, or the B1 vector, maps to this vector. So let's see what happens to B2. T of B2 is the same thing as B2 applied to A, which is 6, negative 3, negative 3, 2, negative 2, and 5. So that's going to be negative 12 minus 15, negative 27, and positive 16. So it's still in the same vicinity, except it seems to have gotten stretched and stuff. So negative 27, 16. So maybe a little bit flatter than the other one. Oh, maybe it'll be going, it might be going this way. So that maps this vector B2 to this vector. We're still going to get a parallelogram, but the parallelogram is different from the original parallelogram. So that's that. And now we find the area of S. So area of S is going to be the determinant of the absolute value of the determinant of the B1, B2 vector. Let me put these, again, being tedious about this, the absolute value of the determinant of negative 2, 3, negative 2, 5. So that's negative 10 plus 6, negative 4. Absolute value is positive 4. Right? So now, if we just figure out what A is equal to, determinant of A, that's 6, negative 3, negative 3, 2. And that's 12 minus 9 is 3. Is that 3? Is it 9? Yeah, hopefully it'll be the same, right? So this would be, so according to this, area of our resulting is going to be 4 times 3 is equal to 12, right? So like Erica was suggesting, maybe we know how to take determinants of these things. So why don't we find the area of the vectors, since we know the image of those vectors anyways. So area of these two vectors, is going to be these two vectors. Right? And so this is equal to 12. Oh, negative 12, but you want an absolute value, so it's the same. Oh, shoot. It would have sucked if it was different. No, well, this is, I mean, in terms of Calc 3, it probably wasn't very helpful, but this is the example. I mean, this simple example, it's easy to see and stuff. We could do this in 3 dimensions. And in fact, there's another problem that we're not going to do. Hey, this looks like a good test question. So if you have a transformation from R3 to R3, this time your matrix looks like this. It's a diagonal matrix, so it's a nice matrix to deal with. And then we know that the volume of a sphere is going to be 4/3 pi, or is it 4 pi, or yeah, 4/3 pi, radius 1. Then this transformation will actually take the circle and extend it, along the x-axis by A, along the y-axis by B, and along the z-axis by 3 or by C. And then that is a transformation where you can find the area, of that three-dimensional ellipse, also known as ellipsoid. To find the volume of that ellipse, all you have to do is find the volume of the sphere, which is easy to do, and then multiply it by the determinant of A. Yeah, it's 4/3 pi r cubed times A times, well, instead of r, you multiply it times A times B times C. Anyways, this is in your textbook at, I don't know if this is a homework problem. This would have been a good homework problem to give. Okay. Not today. All right. So here we are again with 3 minutes left and a whole section to cover. I think last time I just copied and pasted this into our notes, so it's in your notes already. Anyways, the idea here is that for your linear transformation, you get a linear transformation, and then you can define a matrix for it. And that matrix is actually dependent. We ignore the dependency, but it's actually dependent on the basis for the space that you're in. And we take that for granted because in these examples that we did where we found the matrix or the matrix was given to us, we're assuming that that matrix A is the matrix that comes from the standard basis. And the standard basis in 2 dimensions is your ij, in 3 dimensions is your ijk. But the thing is that you don't have to be restricted to those basis vectors. And so they have the subscript for the basis vectors if you create a new basis. So I did not. So yeah, we have a minute left. Yes. Yeah. So if you want to start making your sheet of notes for the test, you should start making that now. So the test is a week from today. Yeah. Also, in the past, I've always dressed up as something really scary. Yeah. Did I post the review? Where should I put it? I'll put it here, where it says review. Um, I probably do, but I'll make one up. So, should I put it under today or Monday? So, review sheet is what it's called. So yeah, I usually dress up like a math test. And then I would scare people. Maybe this year I'll be the Jacobian. All right, so I think that's it for today. I'll just post this stuff up and then you guys can look at it. I'll try and make a video for set 4.5 and do some examples.